Hi, this video is being recorded as a part of UCSD TA application. So today's our topic of discussion is binary search. So let's start with the problem statement first. So we are given a sorted array of numbers and our goal is to find the specific number in the array. Now the requirement for the binary search to work effectively is that the array must be in the sorted order. Now why do we prefer binary search over a linear search? It is because it is an efficient algorithm providing the time complexity of big O of log n compared to big O of n in the linear search. Now to understand it, let's first understand the pseudocode for it. So to perform the binary search, we divide the array into half repeatedly until we get the desired number. So the first step is that we set two variables, the low and high. The low is the first index of an array and high is the last index of an array. Now we run a loop till low is less than equal to high and we repeat the following steps. So what we do first is we set a new index mid which is equal to the average of low and high. Now we check the value at index mid. If it's equal to the desired number, then we are done with searching the element successfully and we can stop the search. But if the value at index mid it is greater than the desired number, it means we know that the desired number would be on the left hand side of the mid index because the array is sorted. So we set our high is equal to mid minus 1. That is, we simply reduce our search space to the left half. Similarly, if the value at index mid it is less than the desired number, then we can find the number on the right side of that mid index. So we set our low is equal to mid plus 1 and we again reduce our search space to the right half. We repeat these steps 3 to 6 until we get the desired number, and if we don't get it, it means that the number is not present in the array. Now let's understand with the visualization. So suppose we are given this array of 8 elements and the task is to find the search element 9 which is at index 4. So starting the algorithm, first we will set the low and high. So low would be the first index of an array and high would be the last index of an array. So here they are 0 and 7. And we calculate the mid, which is the average of low and high, which is set to 3. So this is low, high and mid. Now we see that at the value at index 3, which is equal to 7, it is less than 9. It means that the 9 can be present on the right hand side of mid. So we update our low to mid plus 1, which is 4. So this is a new low and this is a new high, which is equal to the last one. Now the updated mid would be the average of new low and new high, so which would be 5. Now the value at index 5, which is 11, it is greater than 9. So we know that the element we need to search would be on the left hand side. So we update high is equal to mid minus 1. And so the low and high are now 4. Now we again find the new mid, which is again average of low and high, which is 4. Now here we can see that the value at index 4 is equal to the desired number. So we are successfully done with finding out the number. Now let's discuss about the time complexity. So as we discussed earlier, the binary search is an efficient algorithm and it provides the time complexity of big O of log n, where n is the size of the array. So let's work it out to find out how it is big O of log n. So we can see that initially the length of array is n. Now after the first iteration, we reduced the search space to half. Like here we can see that initially the search space was all the 8 elements. Now after the first iteration, we have reduced the search space to only these 4 elements. So we have reduced it from 8 to 4, which is we have reduced it to half. Now after iteration 2, we again reduced search space to other half. So like it is done to n by 4, which is n by 2 square. So like this, after k iterations, the length of array to search would become n by 2 power k. So and we can say that after eventually k iterations, the length of array where we need to now search will become 1. Like here you can see that after k iterations, the last was only one element was present in the search space. So we equate n by 2 power k is equal to 1. And from this we find out that k is equal to log 2n. Now, as each iteration takes the constant time, so the time complexity of binary search is big O of log n. So that's all about binary search. Thank you.